In this problem, we have an infinitely long wire with linear charge density lambda. Now this is a symmetric enough situation that we can use Gauss's law because the wire is infinitely long. Were the wire of finite length, we would have to actually integrate to get the electric field. And that's the problems that we call electric field due to a rod. So for this infinitely long wire of linear charge density lambda, we want the field outside, say here. So we draw for long, skinny charge distributions, we draw our Gaussian surface as a cylinder. And the reason for that choice is because the electric field lines point radially out from the wire, and the area vector of that Gaussian surface is parallel to E, and that allows us to apply Gauss's law in our working form. So Gauss's law says that E is equal to Qn over A epsilon naught. We'll let the radius of our Gaussian surface be R and the length be L. Now, even though the wire is infinitely long, the Gaussian surface is not infinitely long. It is of finite length L. So the amount of charge inside our Gaussian surface is this amount of charge chopped off by the Gaussian surface. That would be our Q in. And we can see that that just exactly equals the charge density times the length of the Gaussian surface. The area through which the flux passes, that where the area vector is parallel to the electric field vector, is only the curvy side of this Gaussian surface, not the top and the bottom. So the curvy side has surface area 2 pi r L epsilon naught. Now the L always has to cancel because the length of the Gaussian surface is completely arbitrary. And we're left with lambda over 2 pi epsilon naught r, or 2k lambda over r. So the electric field due to a long, thin wire of charge is proportional to 1 over r, unlike a sphere or a point charge where it's proportional to 1 over r squared.